going to study this maybe in more detail later on. Okay, now this is one type of memory, that is an SRAM. Now we study another memory. I also told you, now we go to another memory technology, that is STRAM, Spin Transfer Task Random Access Memory. And typically, it's like the access time is also like fixed, but the access time and the access power is now determined by the content of the data. Like the latency to write a zero, the latency to write from parallel to anti-parallel or anti-parallel to parallel state is different. If you remember, I told you that now which layer we have used? Fixed layer, and then movable layer. Which state is this? Parallel state. So okay, parallel state means low resistance. And if we want to change the magnetic orientation of the movable layer, what we need to do? So there is some associated circuitry here on this side or this side, some access transistor. I'm not going into much detail here. Maybe it has I will know of these circuitry or details. So if we want to change the magnetic orientation from parallel to anti-parallel, so from which direction we need to pass the current? From right to left? Right to left. So when we pass right to left current, so it will change from, the magnetic orientation will be changed from parallel to anti-parallel. And if you want to switch back, we have to transfer the current. Now, the problem with this is like this, that the latency, so now we have two. We have P to AP and AP to P. So from P to AP, P means parallel, AP anti-parallel. From P to AP and from AP to P, the latency is lower. Latency in energy consumption is low, and from anti-parallel to parallel, latency is and energy is high. Now in this case, okay, now if we have an STT-RAM memory, what kind of optimization can we do with this memory? Think, what should we do? Now if we want to optimize for power, let's assume if we want to optimize for power. But if you consider any data, so data, it means if you want to write 1011, and if you want to write this data, if you want to change the data from 10111, which of the bits are being changed? B3, B2, B1 and B0. It will remain the same. Yes. Remain the same. You don't need to pass the current because it's stay the chain. Now it is the switching. Now it is this chain. So this is from 0 to 1 and 1 to 0. Now these are transitions. Okay, what kind of optimization? Can you think? What kind of optimization can we do with this STT array? Just think. What kind of optimization? I just gave you an idea. How can we exploit this factor? How can we exploit this factor? And so that we can optimize the energy.
सर हम 0 से 1 के ऊपर जा रहे हैं, जब हम कह रहे हैं पैरेलल करना तो एक साइड से हम आए जिस साइड से हमारी
नहीं, what kind of optimization can we do? The energy will use this.
We just shift the bits.
What shift the bits?
The lower number.
Why should we shift the bits?
Then we won't have to do the.
No. We can, like, what kind of optimization I will tell you. From a very high level. If you profile your application, and if you profile your application, if you say that my application has now 75% of zeros and 25% of 1. Now this is a hint. What should now we do? So it means we can do an efficient encoding. We can do an efficient coding. That we can say, okay, now for 0 should be in the low energy state in majority of the time because the switching will be less. This is one kind of optimization that we can do. This is one kind of optimization that we can do. It also depends upon other factor. We can also do another optimization. There is one technique that is called as flip and right. Which is called as flip and right. Actually, in this kind of memory, the write energy and write latency is very high. Let's assume if the write latency is, they say that the write latency is 10 millisecond. The write latency is 10 millisecond, or the power is, let's assume, like 30 picojoule for instance, and the read latency is now 2 nanosecond and 2 picojoule. First we read the data, then we see the number of transitions, and if it is a majority of 0, then we directly store as it is. But if it is a majority of 1, so what we can do? We can convert them into 0 by using inverter and store 1 bit. So it means that if that information, if that bit is 0, it means that now low resistance state. So like now I will explain this with an example. So now 0 0 0 0 0 0 0 0, and now 1 1 1 1 1 1 1 1. How many transitions are there? 8 transitions. Actually, so if this is the old data, this is the old data, and now this is the new data. Okay, the energy efficient state. Now let's assume the energy efficient state. Energy efficient state is logic 0, and energy inefficient state is logic 1. Energy efficient state is logic 1. How many transitions are here? 8. We can say that now we say that now we have invert of data and store the same data. We are not updating any data. Next time we will be reading data and we say that invert, then we will read the same data and invert all of them. Now this optimization is called as flip and right optimization. You count the number of transitions. Okay, now if you do use inverter, so it is 8 bits of data. So it means we are not performing a write operation at all. Why we are not performing a write operation?
जो डेटा है वही
जो डेटा उसको एज इट इज रहने दिए और हमने उसकी इनकोडिंग कर दी कि जो भी डेटा है उसको आप क्या कर दें? इन्वर्ट कर नाउ इट हैज सम कॉस्ट. क्या कॉस्ट है इसकी? वी नीड इन्वर्टर्स. सो एक्चुअली यू हैव टू डिसाइड दैट आपने पहले कैलकुलेट करना है, क्योंकि सारी बात है जब when we want to write some data, so we also want to read the data. So first we need to read the data, then we analyze the number of 1 and 0, and then if you are flipping, you are using some inverters, so there is additional energy consumption. The additional energy consumption first in reading the data, then in inverting the data. If the sum of that is greater than the write energy, so it is a suitable approach or not suitable approach? Not suitable. So now you have to do. So actually when you give some parameter and design problems, so actually I may give this kind of design problems in your OST or quizzes or something. There will be some scenarios. We can discuss this scenario. Let's assume we have an STT RAM. This is an energy efficient state is this. Energy inefficient state is this. The old data is this. The new data is this. Write energy is this. Read energy is this. The inverted energy is this. The number of transition. If you use flip and write, will it make sense? It doesn't make sense. Okay. So this what I want to achieve in this course. That I don't want to teach you course in a very conventional way. It's a very unconventional thing. So we will discuss this kind of optimization. What kind of optimization we can do in order to improve the power efficiency or the performance. Okay. So this is the one kind of optimization. The same is true for phase change memory. So in phase change memory, actually I told you that there are two resistance states. So let's assume we have different resistance states. Let's assume that minimum resistance is 3K, and this is 6K, this is 9K, and this is 12K. So this represents a logical 0, this represents a logical 1. Maybe this is parallel state, this is anti-parallel state. The same concept is true for phase change memory. In phase change memory, the working principle is different, but the concept is same. It also has a low resistance range and a high resistance state. In high resistance state, and in phase change memory, there are two types of states. One is amorphous, and another is crystalline. And I don't remember which one of it is high resistance and other is low resistance. And even this disparity in excess latency, right latency, is also there in phase change. Okay, so in that case, one state is energy efficient state and another is energy inefficient state. The same concept is there. So this architecture optimization that I told you, what's the name of that architecture optimization? Flip and write. So now what you need to do, you can search any paper in the internet and just search flip and write for STT-RAM. Flip and write for phase change memory. You may get some papers and you may read this paper and you will learn more things from there. Okay, that how they actually implement flip and write. Okay, now this one is for STT-RAM and also for phase change memory. Now we discuss another type of memory. Another type of memory that is called as rest track memory. Rest track memory. And we also discuss its like characteristics. Now in rest track memory, we already studied that. Now we have some port position, if you remember. Okay, and then we also have some. What is this? Access port, fixed layer. If you remember, fixed root layer, and then domains. 3, 4, 5, 6, 7, 8. Fixed domain. This one is parallel, anti-parallel, parallel, parallel, anti-parallel, anti-parallel, parallel, and parallel. Okay. So now we have domains. This is D, and actually typically the access port is in the middle. So we need to move the track from here to here, or we need to move the track from here to here. Okay. So this is D7, D6, D5, D4, D3, D2, D1, and D0. Okay. So if we want to access D1, so it consists of a track. Track consists of domains, and if you want, okay. So now the current port position. This is current port position. So the current port position is now pointing to which domain? D3. If you want to access D0, what we need to do?
To shift.
To shift. So apply shift current from right to left. To shift current, so it will be shift. One shift, then D2 will be aligned. So actually after shifting, so it will look like this. D0, D1, up to D7. So what's the shift cost now?
2.
1, 2. Okay. D0. If you want to access D0.
So
1, 2, 3 by 3 shifts. Okay. Now I also told you this is only for a single bit. For a single bit. Now if you want to access some data, so we need multiple tracks. So now this is track T0, track 1, and track 63. Okay, now we can 63, 62, and 0, 0. So this is the most significant bit, and this one is the least significant bit. Now each track has some domains. Now now we have, let's assume this is domain. So this is domain D0. This is domain D1 up to D minus 1. Or we can call it location 0. Location 0, location 1, location D1. What is D? D is the number of domains within a track. So in this case, what is D here?
8.
D is equal to 8. Okay, and there is one access port, current port position. So we can store multiple words. So we can say that now we can store word 0 in the first location, word 1 in the second location, and in the last location, what's the word?
D minus.
How many words can we store? We can store
D words.
D words. In how many parallel tracks?
64.
64 parallel tracks. So let's make it more configurable. So this is T W minus 1 to T 0. So we can store W words. Not D. No, sir. We can store D words. D words, each of how many bits?
64 bit.
W bits.
G sir.
TW minus 1. So W is 64, so it will be 64 minus 1 and 60. Okay? Now to access this data, how many access ports we need? We need an access port from here, access port with here, and access port with access port. Okay? And all of the tracks move in a lockstep manner. Like we have current port position is here. Okay? So when we want to access all the bits of W1, so all of the domains will shift in parallel. Now if we want to access, so let's assume the current port position is pointing, to location I, and the desired location is J. The desired location is J. Then what's the shift cost? Shift cost is absolute of I minus J. Okay, now what kind of optimizations can we do with this rest track memory? One optimization that I told you, if you remember.
flip कर दिया data.
No. I told you, na?
Reverse कर दिया, sorry.
Okay, now we call it not flip. What kind of optimization? In order to reduce the shift cost. वो मैट्रिक्स मल्टीप्लिकेशन की मैंने बात की थी. Row measure order and the column measure order. First to row measure order and then in column measure order, and then we can do this kind of optimization. We can also do another type of optimization here in the memory controller. We can do some optimization in the memory controller. I will explain this. Now let's assume that we have some requests in the request buffer. Now this is the request buffer. This request buffer is a buffer that is typically available in any memory device, and it can contain multiple requests. Okay, so memory can also be used to serve multiple requests at the same time. So let's say we have some request buffer. Okay, and now we have some requests, and I'm giving the addresses of the locations of a rest memory. So now this is a track, we call it as a DBC. We call it as DBC, domain block cluster. So it means now at a very high level we abstract it. So we have location 0, location 1, and up to location, how many location? D minus 1. And location 0 is actually storing word 0, word 1, and so forth, so on, word D minus 1. So it means that this domain block cluster consists of how many parallel tracks? W parallel tracks. Okay. So now let's assume we have a request buffer 5, 3, 7, 13, and 2. So these are the requests. These are the requests in the request buffer. So if you implement a FIFO policy, first in, first out. First in, first out. And let's assume that the current port position is now, let's assume at location 0. So access 5 address, so it needs to move from location 0 to location 5. What will be the shift cost? 5. 0 minus 5. 5. Shift cost. So the shift cost is now from 5 to 3, what is the shift cost?
2.
2 to 7, what's the shift cost?
5.
5. Okay, now this is the current port. Now the current port is in now location 5. 5 minus 3, 2. This is 5 minus 0. Then the current port is now, current port is
5.
0 minus 5. The current port will now move to location 5. Then 5 minus 2. Current port position is now 3. 3 minus 5.
तो current 5 हो जाएगा.
So the current port is 3 minus 5. The current port position will go to 5. No, not 5. 3 minus 7. So the current port position should be then 7. In this case, the current port position will be 13. The current port position will be 2. Okay. So 0 minus 5, 5. Then 5 minus 2, 3. Then 7 minus 13. The current port position is now 7. Because the current port position is 7. Now you move from 7 to 13. The shift cost is 6. And now the current port position is 13. Then you want to move to location 2. When you want to move to location 2, what is the total shift cost? 7 plus 5, 12 plus 5, 10, 12, 6, 18, 29. Okay. What optimization can we do now?
First we read the 2 and then.
Okay, so we can do this kind of optimization with access reordering. With access reordering, so if we say that now if we reorder the access, it's 2, 3, 5, 7, and if you do the access ordering, so we can do the optimization. But it also always there is always a trade-off, because it may also cause starvation. Maybe the oldest request that is lying in the request buffer for a very long time, it will be stored for a long time. So it should not. So here can we, now this is a very simple example with the access reordering in the restrict memory. With access reordering, if you do the access time 2, 3, 4, so actually what will be, it's very simple. The shift cost will be 2, the shift cost will be 1, will be 2, the shift cost will be 5 minus 7, 2, 7 minus 6. Total shift cost will be 3, 5,
15.
13.
13.
8, 10, 11, 12, 13. Because now we are moving from 0 to 13, because in the top to bottom. Okay? So actually now it's whenever when you want to design a controller for us. Now this is a very simple example. Now you say that it is a request buffer, but actually when it's a request buffer, so there is also a timestamp associated with each request. A timestamp. Okay, now this is in the request buffer. At which time it is coming? Maybe this is coming at T0, maybe at T1. This is T2, maybe it's T3 and T4. So actually there is a timestamp also available with the request buffer. So if you want to design a controller for the restrict memory, so now you have to consider the timestamp at which arrival time. Now then you can have a round robin scheduling. You do the access reordering, and if the request stays in the request buffer for a very long time, you can also have some kind of a threshold. So then you should prioritize it. We should prioritize it. That it stays that you can have a say. But if a request stays in the request buffer, for instance, for maybe 20 nanosecond or 30 nanosecond or for 30 cycles or for, they should be served first. Its priority should be increased. So you can design an efficient memory controller for the RTM. This is one kind of optimization. This is one kind of optimization. This is the kind of the optimization that when you don't know the access pattern in advance, because you don't know the access pattern in advance. You don't know the access pattern in advance, and actually new requests are coming and new requests are coming in the request buffer at different time instance. And at runtime you decide that which request should be served first and which request should be served later on. Okay, so this is an access. So these are different type of optimizations. These are different type of optimization that we need to consider when designing a restricted memory. And such similar kind of optimization we will study in other type of memory technologies. Okay, now we have another problem. We have another problem with the restricted memory. This is one kind of optimizations that we can do.
One type of memory that we never came up with.
What?
Resistive RAM. We never talk about that.
I'm not in this part of that because I didn't study more and more detail. But it's just some sneaky current, I think, so some kind of a current. But I never studied this in more detail. Okay, the second type of optimization. The second type of optimization that I told you that let's assume if you want to multiply two messages. I just repeat for some students who were present in the previous class. So now let's assume if we want to multiply two matrices, A cross B is equal to C, and these are some matrices. A cross B is equal to C. Okay, now for this, okay, now you have to study this flip and write. To search flip and write, you can search on the internet, you can read some papers regarding that. I told you the concept of flip and write. Now, for this problem set, we have one paper that is called as optimizing tensor contraction with restrict memory. I'm the author of this, one of the author of this paper. So you can search on the internet and you can. So but I'll just give you a very high level overview of the idea that what kind of optimization did we do in this paper. So now if you have say A cross B is equal to C, so this is a matrix multiplication. So now we have a matrix A cross matrix B cross C. So this is A00, A01, A02 and so forth, so on, and maybe A63. I'm just keeping the size of fixed. So now we are assuming that we are storing this data in one rest stack, in a group of rest stacks that is called domain block clusters. Okay, and that has 64 locations. So we have how many parallel tracks? 64. So how many tracks are there in the domain?
0 to 63.
How many domains in a track? There are 63 domains in a track. So D, there are 60.
0 to 3.
This is location 0 to location 61. So now we are stored. And the size of this may be 32 bits. Let's assume we have 32 bits. So how many parallel tracks we need? We need 32 parallel tracks. Okay. So now B00, B01, B02, and so forth, so on, B63. And then B10, B11, okay, and then B63. So actually, typically in previous type of memories like in DRAM, what they were storing? They were storing the data in the row major order. They are storing the data in a row major, like it is stored in one row and it is stored in one row. This is called as row major order. Now, if you use this row major order, this optimization is not good in restrict memory. What optimization do you do? We stored, okay, why not to store the data not in this format but data in this format? That we store the data of matrix A in row major order, and we store the data of the matrix B in column major order. So we can do the optimizations. So because if you want to complete this data, so what we need? We need to multiply the first